Hello, Math 119 students. This video is about confidence intervals. We're going to do a computer simulation for some t-intervals. So the objective is to determine what is the meaning of the level of confidence. So let's begin with this example. So let's say we have a normal distribution with a mean of 50 and a standard deviation of 10. And we'll use a confidence level of 90% and a sample size of 10. So we will simulate multiple t-intervals and see what happens. So remember, the confidence level is 90%. So what does this graph show? Well, the little green, so we have 100 of these little bars, you can call them. And the green dot is the location of the mean. So if we can put the cursor here, so it shows here's the first simulated confidence interval. So the mean, remember the population mean is 50, but the mean of the sample, the simulated sample is, it says here, 52.892. And standard error is 2.852. The lower limit is 47.665. The upper limit is 58.119. So the confidence interval, because 50 is in between the lower limit and the upper limit, the confidence interval contains the true population mean. So the ones where the confidence interval does contain the true population mean, those are the green bars. The red bars are the intervals, like here's a red one here. The mean was 54.205. The lower limit is 50.721, and the upper limit was 57.688. So 50 is not contained within the limits of the confidence interval. So those ones are red. So we want to, out of the 100 simulated intervals, what percentage of them are green and what percentage are red? Well, it tells you right here. The ones that contain mu, 87 out of 100, that's 87%. Well, the theoretical percentage should be about 90%. So let's try 100 more simulations. Okay, actually this time we got only three red ones that don't contain mu. So overall we have 92%. Let's try 100 more. Okay, this time we had a lot more red ones. We have, I think, 11 red ones, so that would be 89% green. So our overall percentage is 91%. So the theoretical percentage that should be green would be 90%. Okay, here's something else I want to do. I want to see what happens when we don't satisfy the central limit theorem requirement. So the central limit theorem requirement is that you either have a large sample or a normal distribution. Well, what if we don't satisfy that requirement? What will happen? Well, let's see. We can simulate that. So we'll go to confidence interval for a mean. But this time, instead of a normal distribution, in the first example, the population distribution was normal. Now we'll look at it if we have a right skewed distribution. So our population we're sampling from is right skewed. So now with this example, we won't satisfy the central limit theorem because we have a non-normal population and a small sample. So let's see what happens. Okay, with the first 100 simulations, we got 91 out of 100. So that would be 91%. And theoretically, we're simulating 95% confidence intervals, so we would expect to get about 95%. Let's try 100 more. Okay, this time we got, let's see, how many red ones do we have? we got 91 green and 9 red. So our overall percentage is 91%. So you can see when you don't satisfy the central limit theorem requirement, your percentage tends to be a little bit low. Okay? So the long run percentage probably won't equal 95%. It'll probably be a little bit low. Okay, the next thing I want to do is, let's say we have a non-normal population, but we have a large sample size. So let's increase the sample size to 40. So now we do satisfy the central limit theorem requirement because we have a non-normal population, but we have a large sample size. So let's see what happens. Okay, so we're pretty close. We got 94% out of 94 out of 100 green. So let's try 100 more. Okay, so now this time we got 96 out of 100. So our overall percentage is 95%. So now you can see we're with our simulations, we're closer to 95% than when we had a small sample. Okay, so that's the last one I want to do, and that's what I wanted to show with this simulation.